You've probably often seen a pattern of water ripples. Such a pattern is similar to that of invisible radio waves transmitted from antennas. Most radio antenna systems are designed with three main problems in mind. First, the system must either radiate or else receive radio waves for a particular use on the surface of the earth or in the air. Secondly, the system must have maximum power radiation. And finally, the system must be designed to meet particular conditions of use. For example, when airborne, it must be aerodynamically clean, like the pickaxe antenna within the vertical stabilizer. It is in a streamlined housing and therefore allows a smooth, easy air passage around it. And since today's flight operations depend on an elaborate system of radio communication with the ground, let's examine ground antenna systems first. Every radio wave pattern has three-dimensional qualities which can be represented in a hemisphere. Here is the vertical plane, while this is the horizontal plane. Non-directional radiation can be symbolized by the rays from a light bulb. On the other hand, these rays can be concentrated and directed, as in a flashlight, for directional beam patterns. The kind of pattern which is needed for a particular communications job determines the type of antenna to be used. Let's assume clear reception is needed between two specific locations. The problem may be solved by using a collinear array antenna. Generally, this antenna is stationary. Physically, it can be quite small when very high-frequency channels are planned. The collinear array has two or more elements on a common axis. These elements are a half wave in length. They receive electrical signals of equal strength fed in phase. Maximum energy radiates from the center of the elements, with the strength gradually dropping to zero at the element tips. The same transmission takes place on all sides of all elements. Thus, the transmitted radio wave pattern resembles, horizontally, two paddles projected from both sides of the array. Vertically, however, the pattern has the shape of a donut. The broad pattern is produced by a small number of elements. The collinear array can be made even more directional by adding more elements. These added elements sharpen the wave pattern. The result can be compared to whittling down the width of a paddle. When, in addition to horizontal control, vertical directivity is necessary, another antenna, the broadside array, can be used. Like the collinear array, the broadside array is generally stationary. The array is made up of many half-wave elements. These elements are formed into several levels, much like the rungs of a ladder. Let's consider only two levels. When energy is fed in phase to the elements of the lower level, the result is, of course, a collinear pattern. And now, let's energize the upper level of elements. It is these waves which cancel some of the radiation from the first level of elements. The half-wavelength spacing between element levels makes possible this cancellation. As you see, the effect of condensing the wave pattern by using several levels of elements serves to increase the energy in the desired directions and gives greater gain to the beam. It's like focusing a flashlight. Adjust the lens and the beam is concentrated. Returning to our antenna patterns, there are several ways of obtaining sharp control, both horizontally and vertically. The end-fire array antenna is one of them. Physically, the end-fire array resembles a broadside array laid on its side. There are several rows of elements, one behind the other, but operationally there is no resemblance. Each row of half-wave elements is energized out of phase with the next row. With such energizing, the wave pattern is compressed and channelized. maximum wave radiation is sent in two directions. But should your problem be to transmit energy in just one direction, an answer is the parasitic array antenna. In this array, the elements are aligned like those in the end-fire array. When two elements are used, the only element connected directly to the transmitter is called the driven element, which is a half wave in length. The second element is called a reflector and is longer than the first. Let's symbolize the driven element with a fluorescent tube and the reflector as a mirror-like surface. Without the reflector, light is radiated in many directions. But when the reflector is used, the radiation is reflected back and added to the radiation already moving in the desired direction. Thus, the final result is a greater amount of radiation in one direction and almost none in the other. Generally, with the driven and reflector elements, a third element called the director is used. There may be one or more. Its function can be compared to a lens, which concentrates and directs light. Because of its length and distance from the driven element, the director element concentrates the energy it receives. Actually, this is the operating shape of the wave pattern. Since the parasitic array is generally small and compact, it can be made to rotate, quickly pointed in any direction. Its useful distances, however, are limited. But when such wave patterns are to extend over transoceanic distances, then a different type of antenna is usually employed. This type consists of two or more half-wave elements which are connected end to end. It is called a long wire antenna. The elements are energized out of phase. Such out of phase energizing produces a pattern of about this shape. Considering one of its planes, such as the horizontal, reveals that it has 4 lobes at an angle of about 45 degrees with the wire. As more half-wavelength elements are added, minor lobes appear, and the angle between the major lobes and the wire decreases. The longer the wire, the smaller the angle. Such an antenna can be made unidirectional by adding a resistor at the end of the wire, which thus reduces the wave lobes opposite to it. The resistor is grounded. In this antenna, the resistor dissipates the energy which would create lobes opposite to it. Thus, the effective radiation is in the direction of the resistor. A further development in the construction of this type of antenna is the addition of a second long wire at an angle with the first. The combination of the radiated energy from both wires of the V antenna produces a wave pattern with greater directivity. Now then, to reach the desired transoceanic point, this wave pattern is projected toward the sky, where it hits the ionosphere. So, the main job of the long wire or V antenna is to beam as much energy as possible into the sky at an angle so that the beam can be returned to the Earth at the desired point of reception. As you remember, while the collinear array antenna is basic for short distances, the long wire and the V are also considered basic for transoceanic communications. And when such a pattern needs to be made very narrow, another type of antenna is generally used. 2 basic V antennas are placed end to end. Then, add a resistor here. Such an arrangement is called the rhombic antenna. Here the resistor does the same job as in the single long wire. The combined energy from both V antennas radiates in the direction of the resistor. Such a design, therefore, produces a much more directional pattern. Yes, it's truly pinpoint pattern projection across the ocean. But this ground antenna system, like the others you've seen, may be used for communication with aircraft. So let's analyze aircraft antenna systems. Every aircraft antenna is either attached to the exterior or is recessed within the aircraft structure. All radio wave patterns are affected by the position of their antennas. On older aircraft, the antennas were placed wherever space and convenience allowed, such as here, 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 and here. They created vibration and built up drag. As aircraft speeds increased, for example, at 600 miles per hour, the combined drag of exterior antennas could amount to nearly 1,000 horsepower pulling in the opposite direction. Today, most jet aircraft have recessed antennas. These may be located in many different spots, such as the compass loop in the nose, the compass sense in the cockpit, and the VHF command in the vertical stabilizer. Because of its appearance, the antenna is called a pickaxe. It is a top-loaded quarter-wave antenna. From it, a pattern can extend in nearly all directions and thus reach ground control stations. While all aircraft have a radio set for command purposes, so too do they carry a radio compass. Its antenna receives energy within a particular pattern for air navigation. The antenna system is generally mounted forward under the pilot's cockpit. It is composed of a loop antenna and a sense antenna. The signals received by both are combined into a reception pattern resembling a cardioid. With such an antenna system, it is possible to readily determine proper flight direction. In high-speed aircraft, the navigation antennas are usually mounted in the canopy. The sense antenna is molded in the plastic dome and is like a broad wire screen. In some aircraft, the loop antenna is under the dome in back of the pilot. The combined pattern of both antennas is exactly the same as in the old-style exterior mounts. Many aircraft have a marker beacon receiver. It has a specialized antenna system designed to receive a particular pattern in a particular manner from a ground station. The marker beacon antenna is mounted on the underside of the aircraft and may consist of a half-wavelength wire. Every antenna system has a reception pattern similar to the pattern which it can transmit. Such an antenna system receives ground-transmitted energy within a wave pattern shaped like a teardrop. But this wire antenna causes drag. Therefore, on high-speed aircraft, the antenna system is recessed. Generally, it is located between the wing and tail assemblies and is shaped like an inverted miniature bathtub. The receptacle acts as a reflector, concentrating a greater amount of energy toward the antenna rod. The reception pattern is still like a teardrop, but more directive, sharper than the old-time outside-underside wire. Now, as you recall, while the command radio is basic for all aircraft, the liaison radio is also basic, but only for aircraft having a radio operator. A fixed wire extends generally from the stub mast to the vertical stabilizer. Its job is of course twofold: sending and receiving. As there's no way of knowing where the ground station is located, a non-directional system is necessary. And so with the exterior mounted antenna, the wave pattern resembles a very rough figure 8, as seen in a cross-sectional view. As with other antennas, here too, drag is considerable, and on fast-flying jet aircraft, the antenna is recessed. Two of the possible locations are in the wingtips and in the vertical stabilizer. When it is recessed in the wingtips, a well-defined pattern is produced. When the same antenna is recessed in the stabilizer, it is usually in a vertical position. The resulting pattern is again well-defined, but is oriented differently. These typical antenna systems and their respective patterns for both aircraft and surface use are the key to all military communications. The speed and accuracy of these communications around the world depend on skilled communications personnel.